So yeah, as he said, I've been working as mostly a commercial security consultant for about a decade. And I started very low level, code review, that kind of stuff, and slowly worked my way up. Right now, I do security architecture, protocol design, like development process re-engineering, and security strategy work. This talk is mostly going to be kind of looking at some of the stuff that's higher level up the security stack, which is stuff that every development shop needs to deal with, and I think it will hopefully be useful for you guys. Over the past couple of years, I've moved out of doing commercial work, and now I mostly work on security for high-risk users, which mostly means looking at security software, looking at the tools that we tell people will keep them safe online. It's mostly a lie, but you know, we try. All right, so 59 slides in about 40 minutes. Let's do this. Let's try to do this. Let's do that instead. All right, so what is security? A lot of people think that, oh, if I don't have any cross-site scripting bugs, any CSRF bugs, any SQL injections, I'm secure, right? No, you have no idea what you are, because security is not a property of the software at a low level on the metal. Security is not specific to resistance to specific classes of bugs. It's not about what testing regime you ran. It's not about your code. Security is about whether the humans who are using your system to do something can do what they want in the presence of other hostile humans. This doesn't really matter if it's a Rails application or the checkout process at your grocery store. Either way, if somebody manages to drive a tank through it, you have serious problems. If you want to know what you are, to know whether you're secure, you have to know what your humans want. This turns out to be a somewhat complicated prospect. We use security objectives to talk about what people actually want. So I'm going to talk a little bit about what a security objective is. Security objectives are what we decide we really care about at the requirements level. If you have an application and you're looking at it before you start writing code, before you start actually designing code or doing architecture work, at some level somebody sits down and says, hey, we want this application to do X, Y, and Z, and that's why we're going to give you this wheelbarrow full of cash to write it. Well, maybe they don't give you a wheelbarrow, but if you don't know what it's supposed to do, you're not going to start writing code. So security objectives operate at that level. They take the form of when some bad actor decides to or attempts to make something that we care about bad go wrong with our system, the system should respond by doing some sensible thing. Now, one of the problems, one of the problems is that no one actually writes security objectives. This is really tragic. In the course of the past decade, I've probably read 100 requirements documents, maybe 200, I don't know. The good ones all have sections which say security in big letters. I always skip those sections because they never actually tell me anything about the system. It's always, the system should be secure. The system should be secure against these kinds of, no, I don't care. It never says, what do we want the system to actually do? What does secure mean in the business context of this system? What can actually go wrong? What do we want to do about it? So a lot of the time, the way we figure out what the security requirements are for a system is we get a bunch of smart people in a room, and they all sit down at a table, and they talk about what could maybe go wrong. And there's no real structure there. And that's if you're lucky and you have smart people whose job it is to just think about security. So one of the things that we'd like is we'd like a tool that lets us take that process of the smart folks sitting around the table, take that process of figuring out what can actually go wrong with our system and what we'd actually like to do about it, and we want a way to formalize that. So threat models are basically how we solve this problem. Here's a definition. A threat model is a formal, complete, human-readable model of the human activities and priorities and of the security-relevant features of the in-scope portions of a system. I'm going to now explain what that actually means in human terms. So A threat model is a formal model. I don't necessarily mean formal here. If you notice, a couple of words on is human readable, but I mean that we need to be able to reason about it in some way, because we need to be able to look at it and say, well, is this valid or is this not valid? If it's completely up to interpretation as to whether or not the shipped system is in compliance with the threat model that you said you were gonna ship. When somebody goes to a senior vice president with a bug and says, or to the client with a bug and says, you need to fix this, see here, the threat model says, then you end up in a 4-hour argument about what the threat model actually says and what the meaning of is. So you want some kind of formal structure that actually lets you decide. You'd like to know that you're finished. One of the big issues with the bunch of smart guys sitting around a table is they come up with some stuff, and they come up with some more stuff, and they come up with even more stuff, and then it's time to go get a beer. So we must be done, right? Because that's how security works. It stops when you start drinking. So no, we need a system that's going to tell us whether or not we're done. We need a system that lets us know when we've finished. It needs to be human readable. I don't know if any of you have ever heard of Zed, the software provability language. No, good. Dear God, don't ever get anywhere near it. You will get nothing done for weeks, probably 2 or 3 PhDs even. Yeah, so we need a system that we can actually not necessarily read straight off the bat, but explain to normal people. It needs to be a model. We need to be able to say, what if this happens? What if this changes? Kind of how does this thing actually work? I can't just have this is a language which we describe something in. I need to also be able to again, reason about it in certain kinds of ways. First off, we care about the human activities and priorities. This is what the humans actually value in the system. It's not just about the technical details. This stuff has to actually be in this model, which is the requirements layer. It also needs to include all of the security relevant features of the actual technical system. This is not all of the features necessarily. You sometimes get stuff where it's like, wow, that's a really neat caching algorithm. It has no security implications. This is probably a lie, but we want some gesture there. In scope, we need to have a structure for scoping, a structure for understanding this is our web application. That is a DNS server. We don't need to threat model the DNS server because it's a DNS server. It's just going to do what it does. So I want to talk a little bit about how you actually make a threat model. I'm going to go through this fairly quickly, but I want you guys to at least have an idea of the kind of process that I'm talking about. So when I talk about why you might want to do this, it'll make a little bit more sense. So we've basically got 6 steps. Like every other process, this is recursive and iterative and living documents and all of that nonsense. But this is roughly what it looks like. You start with actors, assets, and actions. You go through understanding what the threats to the system are. You write your security objectives that you can then put in that requirements document so I'm not a sad panda when I show up. Then we talk about data flow diagrams as we move into the architecture, use cases for how the system actually does what it does, more detail in the use cases, and then understanding how the thing breaks. So let's start at the beginning. We have actors. Actors are humans most of the time. Sometimes they're autonomous systems. Sometimes they're rogue AIs that are going to attack you and steal all your cookies. But mostly they're humans. We have assets. Assets are the things that we actually care about concretely. A password is not an asset unless you are a password management system. Because honestly, I don't care about your password. What I care about is that I can stop other people from getting into my account or get into your account. So these are the things that the system is actually designed to deal with. We have this formal structure, which is this matrix here, and this gets into the kind of formality and completeness stuff, where we say, okay, an actor can do a thing to an asset from this controlled vocabulary. A normal user can create a blog post if they own the blog. So create, read, update, delete. The execute and configure are only relevant if you have weird cases where you have assets that are also executable or whatever, but you could ignore them for this context. So this gives me a basic model. If something is yellow, and sometimes that means there's some set of rules. You can't just always create a blog post. You can only create a blog post on a blog that you're supposed to have access to, have write access to. So this lets us basically represent in a fairly simple and straightforward way, but with enough detail that we can actually reason about it, the human business rules of a system. So next, we go from this to threats and security objectives, now that we have a model of the requirements. So a threat in my world is any negative outcome in a human process the system is built to support. So if I can either stop you from doing a thing that you're supposed to be able to do, or do a thing that I'm not supposed to be able to do, that's a threat to the system. That's a negative outcome. Once we build a matrix, we don't generally take into account who is doing this, because in our experience, and me and the other consultants who've worked with this process, it turns out that it actually doesn't really matter who does a thing for how bad it is. So we skip that step to save ourselves some trouble, and we just kind of rank these in terms of how important they are. Once we have an understanding of which negative human outcomes we really care about, then we can start saying, here's our list of security objectives. We don't want some bad person we're especially worried about to be able to do this really horrible thing, like create a blog post when they're not supposed to be able to do that because it's somebody else's blog. And the system should respond by doing something sensible. In this case, it should thwart the attack. The attack should not succeed. You might also say, well, I can't actually stop them from reloading the blog thousands of times a minute, but I can rate limit them. And so I want to constrain a denial of service attack that way. You don't always get to just prevent attacks. Sometimes there are risks you have to accept. So after you go through this process for a real system, this gives you a set of security objectives that you move into your requirements. Next, we go into the architecture. Data flow diagrams are a way of representing the structure of a system that lets you actually think and reason about what's going on. They're a lot like network diagrams. They're a little bit less formal. They can occur at multiple different levels. This is a very simple data flow diagram. Trust boundaries are obviously really important if you're trying to model the security. So what we have here is a set of external interactors, the user, an anonymous somebody on the internet, and an admin, all interacting with a blog server which has some data store, and there's a trust boundary around all of them. If we kind of zoom in a bit, we see that we've actually got a few different trust boundaries because we have a few different front ends. We have actually a second data store that's caching something. This view of a system gives us enough detail that we can walk different flows of what's actually going on in the system through it without kind of losing too much detail for what we need for a security model, because we know where the trust boundaries are. So, and again, apologies for going so quickly. I just want to kind of zip through this so we can talk about how it impacts you. Use cases are how the system actually works, right? You probably, certainly if you're using Agile, you have a list of user stories of different tasks that the user is going to take in the system. If you're integrating this with Agile, you can reuse a lot of that stuff. You're going to have some things in here that we find out, for instance, when we look at how intended actions actually occur. Okay, so you've probably got a login user story, but you probably don't have a load a page user story because that's just sort of assumed. So when we're modeling the use flows, we end up digging in a bit deeper, pulling out things. It's like, oh, this is the basic story about how users interact with servers. This is what the page flow is through the caching layer and the back end and the database. And now that we've got that in a specific use case, we can reason and talk about its security properties. Other things that you see on here are kind of pre and post conditions. This lets us talk about if the user is going to log in, we need to know that after they've logged in, they're now in a different state. They're now no longer anonymous. So this lets us model things that are state changes that happen to users and that kind of thing. And we can talk about how that gets represented and that kind of stuff, and we'll talk about that in a second. Preconditions are also really important because that's the set of things that you need to have already be true before you're going to be able to complete something successfully. Both preconditions and postconditions represent things that use case has to check for, which we look at when we look at detailed use cases. This is basically walking through a data flow diagram and saying, okay, now we send this, the text of a post to the posting interface, and that site parses that and checks it for length, checks it if there are any banned HTML tags, whatever. And at each step, somewhere in there has to be the, oh, is this user logged in check? That isn't actually in this flow, which is interesting. If this was actually a properly detailed data flow or a properly detailed use case for a real system, that could actually tell us something really interesting. We forgot to check one of our preconditions, and now we know that we have a workflow level issue. And this is where we get away from the kind of security is cross-site scripting bugs, security is SQL injections, because workflow issues and business rule level issues don't just magically turn up. If you fix all of your cross-site scripting issues with your framework, you can still, if a login check isn't there, then a login check isn't there. Now, your framework may handle user logins too, which is great, but there are always going to be some business rule stuff which you actually have to write code for. And that kind of check is the kind of thing that threat models are better at finding than just about anything else. And they'll also point at the places, as we look at what the failure modes are and how we understand mitigations, they'll point at places where those lower level issues, like a cross-site scripting issue, could happen. So we have a thing called HAZOP analysis from hazards operations. It actually comes from the chemical engineering world. I'm not going to try and go into it in too much detail right now. Basically, for every step, we say what could go wrong. And this gets us back to that formal model where we can reason about what's happening, understand, have we skipped anything? Have we looked at all of the ways that this can fail? Once we understand all the ways that something could fail, then we can talk about, oh, this might violate this set of security objectives that we've decided we care about. This can be influenced by an attacker of this sort. Okay, now we have an actual bug. And you can find these kinds of bugs before you've actually done anything like any work at the code level. You can find these bugs entirely within the scope of architecture. So this is all a lot of work. And I'm not going to lie about that. It is a non-trivial amount of work to model an application this way. You get out of it what you put into it. This is not necessarily going to be worth it for every application, but it's actually a surprising number of them. And once you're used to it, this stuff goes surprisingly quickly. One of the things, if you've got a larger application and a larger development process, threat models can define security for your entire software development lifecycle. This isn't just about the security testing that you do at the end right before release. This is how you drive security all the way through an entire life cycle. If you don't have a threat model, you don't actually have an idea, even if some informal threat model, it doesn't necessarily have to be as rigorous as this, but if you don't have some kind of threat model, you don't have any idea what security actually means for your system. You don't understand what you're trying to secure. Also, if you don't have a threat model, you don't have a way of detecting business rule violations. I remember at one point I had a client where I showed up, and once we finally got all the business rules out of them, there was a basic conflict where they wanted to absolutely under no circumstances share this very critical customer account information over here and definitely share this critical customer account information with lots of people over here, and they just hadn't actually elucidated their business rules enough to realize that that was what they're doing. So you sometimes get like fundamental requirements bugs that you're only going to catch if you sit down and do this. One of the things that it lets you do is it lets you define security requirements in a single standard form. Threat models are actually as much a tool of communication as they are a tool of modeling and sort of understanding and design. One of the big problems that we see, especially in larger dev teams, is that yes, there is totally one guy who understands, if you're lucky, one guy who understands all of the security implications of the entire system. He's spending all of his time keeping that state in his head as things change. He's not writing any code, and he can't communicate that state with the people who actually are writing the code. So you get this communication breakdown where you get bugs introduced. Having stuff at the requirements level lets you not stumble over that out of the gate. One of the big issues also that we see is having technical teams talking to business teams and getting them speaking the same language. A lot of the time, you don't have a good way of communicating your trade-offs and your security trade-offs with a development team or with a business team. They have certain things that they know about, you have certain things that you know about. This gives you a common language at that level as well. And it also lets you make a case for spending the money to do things correctly. During architecture, this is a critical tool for being able to define an architecture that actually makes security sense. If you don't have some kind of security analysis technique, you are going to design things, you're going to design in bugs. There's a chart which I don't have in here, but it's this great curve of what the cost is to fix a bug versus the time of introduction and how long it's been in there, and it's pretty much exponential. You know, you can easily get to, if you find a bug post-deployment, you know, it would have cost, you know, $5 of someone's time to fix it during architecture or requirements, and now you're going to spend 150 grand, if you're lucky, you know, to fix it after you've already shipped stuff to a customer. Again, this gives you a communication format. In this case, it gives you a way of communicating security and variance. All of the things that, like, in this architecture, we absolutely require that a user can never be in these two roles at the same time, or whatever. You're going to have some set of things that need to be true about the architecture as it's implemented in order for it to actually provide the security guarantees that it claims. Also, because you're looking at a model, it lets you do what-ifs. It lets you do trade-offs. You know, okay, well, we've developed this part of the security of the threat model for this design, and we've developed one for this design. So now let's look at what we're going to have to do for mitigation in both designs, and we can come up with an understanding of relative difficulty. So during development, great, you have a formal list of everything each developer needs to check when they're touching any code path. This is really, really nice to have. Now you don't need to guess at what you need to maintain, guess at which properties you need to check. You've just got a list. And if it's not on the list and it's not a low-level platform issue, you can probably ignore it. This saves your time. You can see the impact and the source of all of the different security requirements. One of the big issues that we run into in the field is that a developer will get told something, look at it, understand something else out of it because they didn't have the logic of the decision, you know, that was not communicated with them. And, you know, they're not stupid. Obviously, they make a probably very good guess at what's going on. But if they, you know, especially in a big, complex, decentralized system, they don't have any of the context to actually understand what that one sentence meant. So with this, there's a single place that they can go back to and understand the context. That also then means that not every developer has to understand the whole system because they can just dive into the parts that affect them as they need to. During test, again, you have a checklist for security tests. You have meaningful coverage guarantees around high-level tests. This is something that we basically just don't have otherwise. Coverage guarantees for security tests. Okay, we checked every code path against buffer overflows or cross-site scripting. Well, okay, great. You found all of the low-level bugs, maybe. But getting code coverage for workflow-level issues, for requirements-level issues, is a lot harder. We basically don't know how to do it. A lot of the time, having this kind of information, if you've got a big, complex like system integration project, it makes high-level security testing possible because you actually know what matters in the system at all. During deployment, same thing. You have a list of the invariants required for the development team and deployment team in the deployment environment, which again is not something that's always documented. You have something that looks vaguely like a network diagram. It's not quite a network diagram, but it's some kind of documentation. Again, this is my perspective as a tester. The number of times that I've come into a shop and said, okay, can I see a diagram of this, you know, like 400 server large enterprise deployment? No, we don't really have one. Here, let me get out a whiteboard and start drawing something that I think is what it is. That's really unfortunate and means that you like lose servers sometimes. Well, it responds to ping. I don't know what data center it's in. This gives you something to at least start hanging that kind of documentation off of. It also gives you an understanding of what's actually really critical in your system. Most of the time, you know, your deployment team is going to know what they get yelled at when it goes down, and they're going to have an idea. This maybe gives them an idea before they get yelled at, which is kind of convenient. During incident response, especially in a large enterprise environment, but even in smaller situations, if you're bringing in outside consultants because, oh God, everything's broken, someone's in there, we don't know what's going on, One of the things which is really difficult is getting those people up to speed quickly because you don't really have very long. So having a model where you can say, here is our security architecture. Here is all of the detail you need to understand what's happening in different code paths in the system is really, really useful if they're trying to figure out how someone got in, if they're going to be able to get back in, what needed to be patched. It gives you built-in triaging of negative business outcomes. Not that you probably can't do this somewhat quickly, but here you've already thought about it when it wasn't 5 in the morning and you weren't madly panicked and the CEO was in the room to tell you that, oh, if that server ever gets breached, then we owe somebody else millions of dollars for legal reasons or whatever. And it gives you what-if scenario analysis. During strategy, same thing. Nicely rolled up high-level understanding of system impact, allows business side to really understand what your security trade-offs are. It gives you that kind of communication. Again, large enterprise view. They do business risk analysis in that world. They have risk models. They can say, well, we can probably take such and such a loss over here and maybe not over here. But historically, when a security team or a development team talk to them, we don't really speak the same language. And this gets us a lot closer to speaking the same language. So a lot of this is designed from a more traditional software perspective. It does work with Agile as well. We have a set of variations that we use for getting Agile organizations up and working with this. So I want to switch gears a little bit now and talk about what I call outcome-oriented security, which is sort of what all of this led me to when I started working with people where when they got owned, it wasn't, oh man, that's really inconvenient. I'm going to have to spend 3 hours on the phone with my bank getting this credit card thing ironed out. And all of a sudden it was, oh man, that's really inconvenient. I was using that arm that just got blown off by some overzealous security team or whatever. So that kind of changed my expectation in a lot of this. Security outcomes are not necessarily always that coherent. One of the big things that we realize a lot of the time in deployment is that, our security as an enterprise, our security as a solution provider, whatever, is not the same as our customers' security. And our customers may have a completely orthogonal set of security worries to us. It takes a certain amount of work to step outside of your security frame and understand what your customers' security desires actually are. A threat model is a good start there. It's not going to get you all the way because you need to actually understand what they're trying to do as opposed to what you think they're trying to do. For the past 30 or 40 years of computer security, we've kind of done some really shitty stuff. We've outsourced and externalized a lot of the cost of security to customers. The patch cycle, the entire patch cycle, is us just saying, well, that looks hard. I'm going to let you solve that. This is really kind of a shitty thing to do to your customers. Don't do it. One of the real surprises to the security community as they've started engaging with actual high-risk users is that a lot of things that we thought were really cool don't actually matter. It doesn't matter how cool your crypto is if somebody is just going to beat you with a hose until you give them a password. For folks who do development work, this is actually a really important one. You don't get to choose what your code does. You thought you were making a cat picture sharing tool, and you have lots of users who are sharing cat pictures. However, it turns out that the biggest indicator for somewhere that a revolution might start is whether or not people share cat pictures there, because that means that it's a place where people actually talk to each other about everyday life. And so if you develop communication systems for normal people or a whole pile of other software, you have a bunch of users who have wildly different security guarantees than you thought they did. At some level, you're maybe not going to design for those users. You can say that those are not use cases that you care about. We'll come back to that. One of the things that we see when we look at how users actually use systems in the field is that there are a lot of times when the security properties we thought we were providing with them aren't the security properties they were actually looking for. So Skype, it turns out, is kind of a horrific tool if you care about security. It's trivial. Everyone in the world can just sort of walk right through it, listen to everything you're saying, you know, watch your webcam. You know, that time when you thought your webcam was off, they can probably turn it on. There's a lot of different stuff. And these vulnerabilities are way more widespread than we thought. However, one of the things that we've seen with people in certainly a lot of the Middle East is that they're still choosing as of, you know, a couple of years ago when I got told this story, we're still choosing to use Skype, even when we said, hey, we've got this really nice, super secure text-based instant messenger client that is actually easy enough to use, and they understood how to use it, because it turned out that the observability of their conversation was less important than them being able to get video confirmation that there was nobody in the room with the other person. That they could, you know, they'd been dealing with being overheard for years. They knew how to communicate in code, but there was an entire other set of security properties that this tool gave them that none of us in the security world were thinking about. It's like, we gave you bulletproof, you know, well, relatively small caliber proof-ish, you know, tools that let you not be overheard. Why would you not? Oh, that's not what you're optimizing for. This brings us to usability and insecurity. One of the best security mechanism that you give people is the security mechanism that people can actually use. As more and more people are motivated to create apps or whatever, or websites that are providing some real security guarantees for people, we run into complexity issues. It doesn't matter what you think you're providing if nobody can actually use it. And we also run into mental model mismatches, and this happens a lot. It turns out that if you spend a lot of time thinking about security or thinking about how a piece of software should work, you have a really clear idea in your head of exactly how it works, of exactly the properties that it's providing, what the trade-offs are, how it breaks, all of that kind of stuff. A user walks up and they start doing something to your software for some ends that they've figured out. They don't have that mental model. If they can't figure out when the security properties that they thought your tool was providing have failed, if they can't figure out how it actually works well enough that their mental model is close enough, and close enough is something that we don't really understand yet in a lot of ways, then they're going to get owned, because they're going to assume that it keeps them safe in entirely different ways than it actually might keep them safe. And they're also not going to take advantage of what it can do for them. Furthermore, and this is true really for all users, but especially for high-risk users, that if they can't do it when they're scared and they're tired and they're in a hurry, then they're definitely going to get owned. Because we don't, when it actually matters, we don't do security when we're, you know, nice and well-rested in a nice, calm environment thinking about security. You know, we do it when we're standing in line at the bank on a, you know, Friday afternoon, poking at this app trying to get something to, yeah. One of the lessons of the past few years is that, and this is why I think all this stuff about high-risk users is actually relevant, is that the way you become a high-risk user online is you annoy someone, and that all of us are potentially high-risk users. And every application that we develop makes a difference to people's total security. We've learned that from advertising systems and all sorts of things all over the place have a huge impact. So we thought that we had this thing called assurance from security, and that was like, all we need to do is audit everything, and we're going to test everything and specify everything, and we're going to know once and for all, and we're going to control environments, and we're going to be sure that something is secure. Well, that didn't work. When you have a big enough distributed system, if any of you have done sysadminning at the like 50,000 server and above level, you realize that, you know, hardware failure is just an epidemiological issue. Like, it happens. It happens all the time. Everything is constantly breaking. Everything is, you know, you're always, you just buy a set of hard drives because you know you're probably going to have to ship some statistically significant portion of them back. It turns out that everything is pretty much always owned. in exactly the same way. In a big enough system, everything is broken. The internet is a big enough system. We need to change a bit how we do security designs. We used to design first in the 90s with this assumption that, well, we're going to put a firewall at the edge of things, and that's going to stop all of the attacks. And because we trust everyone who works for us, then we can do whatever we want inside our bank, right? Because all of the tellers are like totally, absolutely no. So we changed that, and now, especially with web apps, we understand that it doesn't really matter if it's a firewall because everything is coming in on 443 anyway. You know, like all of the stuff that you could possibly want to get at, you just send right in through that firewall. So we've started dealing with this a little bit, but we need to design on the assumption that, yeah, basically every server that we run is going to get compromised. Systems are going to degrade. One of the big things that we can do here is looking at, instead of prevention, moving to a model where we assume things are going to get owned. We try to prevent things. We detect. We notify. We let users look at heuristics for what apps are doing, or what, we let sysadmins look at load heuristics, look at what data is being accessed from where. We build these systems that let our fairly sophisticated kind of human-in-the-loop structures actually do what they do fairly well. And we also stop shipping monocultures. And I know this is one of the things that's really great about scalability and, deploying at web scale and whatever the hell other buzzword you want to use, is we can just ship 5 million of those. Well, that means that as soon as I own one of them, I can own the other 4 million, in not very much time. Heterogeneity is a massive, massive advantage. It may be I have, 1,000 different crap systems, which I've deployed 1 million of, but now I have to, as an attacker, write 1,000 different bugs if I want to own all of you. This is a lot harder as an attacker, so it's a thing that you guys probably want to exploit. So there's an exception, and as this is a language community, this is relevant around low-level bugs. If in 2014 I can still write, if in 2014 I can still write a CSRF bug, a SQL injection bug, a cross-site scripting bug, anything similar, you just lose. That is ridiculous. We can fix all of this. And this is one of the things that I'm really excited about seeing happening in the next few years of platform development and framework development, is that there are entire classes of bug that we can just kill, that we can just get rid of. This is really interesting in terms of looking at the formats that we choose to communicate in. As an attacker, JSON is amazing. Like, you're not just giving me a Turing-complete wire format. You're giving me a nice, human-readable, easily-to-use Turing-complete wire format, and then a lot of the time you're evaluating it. Like, I couldn't write a better bug if I tried. JSON is a bug, just all of it. SQL, when you actually let user or developers compose queries in their, inside the application, is a bug. We can just fix big categories here, and that'll be awesome. So we have a responsibility to the internet, and this is a thing that we've learned in the past few years. We live in a very different world than we thought we lived in a year ago as commercial developers. I can't fix any of the problems of, Rovio and Angry Birds being used to massively spy on people. I can't do anything about that. I can stand outside the gates and shout a bunch. But you guys can, because you guys are the guys who are actually writing those systems. If we do not harden the internet and significantly decentralize the internet, so we don't have those convenient points where you can just, remove SSL here and just sit on that wire and slurp down data, we're going to lose democracy. We're going to lose freedom of expression. You can't have a democratic society where everyone is listened to. Go ask your East German friends, what that history felt like. A lot of this is about fixing business models, not just fixing code. It's about both. This is not an easy challenge, but it is something that we can actually do. We built this system, and one of the interesting things I did earlier this year was I spent a while talking to kind of some of the old gray hairs who wrote some of the first RFCs. And they had really particular politics at the time when they were doing that work. A lot of them still have the same politics. A lot of them are furious now because the thing that they built has been subverted in a dozen different ways. But one of the really interesting things about talking to those folks is that the politics that they had in mind around decentralization mostly bred true for a very long time. They put those values around freedom of expression and ability to communicate and stuff into core protocols that we all use every second of every day. And yeah, now that we live in a Facebook-centric world where if you don't deal with their auth API, you might as well not be routing packets, some of that is broken. But if you look at how we route packets, that hasn't changed. And that still has the same political structure. So that was actually a profoundly hopeful statement for me, that we can actually win this, that we can actually pull together and make this actually happen for real. And I have one last slide, and I'm sorry to end, or two last slides. I'm sorry to end on a bit of a downer, but I was looking through the conference schedule, and I noticed that it was a little white, and it was a little male, and I know this community can do a whole lot better. So here's 26 names that I got from Google very, very quickly of people who could have given great talks here. Any questions?
Well, thank you very much, Eleanor. That was an awesome talk. Are there any questions for Eleanor?
Just a real quick comment. The threat modeling work that I've done is part of a tool called Trike, and that URL up there, octotrike.org, is where you can find more information about the tool. I'll tweet the URL and the presentation deck once I get it tweaked a little bit more later today. Dymaxian is my Twitter handle, so if you want more information, that's where to go.
Hi, do you find that systems developed using Agile have significantly worse security problems than the old waterfall models?
Honestly, they're about the same. It has a lot more to do with discipline of the team, how fresh a lot of the code is, what frameworks they're using, how well they understand the security requirements and the business requirements. I will say that as you move into higher level languages, you get fewer really critical issues. It is hard to, in a Ruby app or a Node app or whatever, it is really hard to screw up as comprehensively as you can with a C++ app. That doesn't mean you can't do it, but it takes more work.
Awesome. Well, thank you very much, Eleanor. That was a fantastic talk. Thank you. Everyone, big round of applause.